Okay, so good afternoon, everyone, and thanks for joining. My name is Deborah Lawler, and I am the federal liaison between the WestFAST and the Western States Water Council. Today's webinar will be recorded and posted to the WestFAST tab found at the Western States Water Council's webpage, westernstateswater.org. Today, we are going to learn about a new online platform called OpenET that is addressing data gaps in water management in the Western U.S. We are going to hear from Forrest Melton. Forrest is a program scientist with NASA's Western Water Applications Office and Associate Program Manager for the Water Resources NASA's Applied Science Program at Moffettville, California. We're also going to hear from Justin Huntington, who is a research professor with the Desert Research Institute. Before I hand it over to Forrest, I wanted to let you know that we will be taking questions at the end of today's presentation. You'll be able to use your chat feature or unmute yourself to pose those questions. If as we go along you do have questions, please capture them in the chat and I'll be happy to read them aloud at the end of the presentations. So with that, I'll turn it over to you, Forrest.
Great, thanks, Deb. Let me go ahead and share my screen. Oh, let's see. I've got, desktop window. All right, let's try that. There we go. All right, are the slides coming across?
Yeah, they are. Forrest, you're in
Thank you.
editor mode. Yeah.
Thanks. Great. So, really happy to be here today to talk with all of you about OpenET. One of the first things, and Justin and I are happy to be here on behalf of the project team. One of the first things I want to point out is the amount of collaboration across the team. And we're lucky to have folks who are part of this team who have been leaders in remote sensing of evapotranspiration for many years. It's also, I think, a really nice example of multiple federal agencies, USGS, USDA, NASA, working together with our university partners, with the private sector, with the Environmental Defense Fund and other NGOs to try to solve something that's been a long-term challenge in water management, which is quantification of evapotranspiration from irrigated agricultural lands and other vegetation types across the landscape. We've been focusing on the Western US initially, which has been a plenty big challenge, but a lot of the accuracy assessment and intercomparison work that we've been conducting, which Justin is going to talk about a little bit later, applies nationally and sets us up nicely to extend this to provide coverage for the US in the future. So a really outstanding team. Something that I think has been a strength of this project is collaboration across the science community. And that's something that's been made possible by our funding partners at the Water Funders Initiative, the NASA Western Water Applications Office, and the other contributors to the project. So looking at the list of folks on the call, I could probably skip the slide, but just to level set really quick. Our work is focused on mapping evapotranspiration at field scales. Of course, water that's applied to a field ultimately either evaporates, transpires through plant leaves and other tissues, or it can percolate and recharge groundwater or run off and return to a local canal or river. So we're really focused on the ET piece of this and quantifying the amount of water that's returning to the atmosphere from the land surface through evapotranspiration. Our primary objective for the project is to produce an operational system to continuously provide data. We use Landsat as really the workhorse for this project, so this allows us to go back in time once we've completed the full architecture and final implementation of all the models all the way back to 1984, but annual coverage from 1985 onward. Data is at the Landsat scale of 30 meters by 30 meters. We're producing data at daily, monthly, and annual time steps, and information is aggregated both to the field boundaries as well as at the original Landsat resolution, 30 meters to 30 meters across the West, wall to wall. We'll be providing a demo of this interface here at the end, but wanted to just sort of state this is really what we're working towards, is this operational system for mapping evapotranspiration across the West. And the reason we're doing it is we know that having access to consistently produced ET data at scale across the West can help us with all kinds of things we've been trying to do for at least 30 years, including development of improved, more realistic water budgets across the West. There's been a lot of really nice work on piloting incentive-driven conservation programs and trying to spur innovation in water management. Having an easier way to measure the benefits and water savings resulting from those investments in those programs, I think allows them to scale much more quickly and cost effectively than we've been able to do to date. Related to that, we want to be sure that agricultural users that have been making those investments in water use efficiency and water conservation are receiving proper credit for those investments and able to easily identify which strategies are actually working and resulting in meaningful reductions in not just applied water, but also evapotranspiration, and then identify the approaches that are both impactful and cost effective and can be implemented at scale. We have also seen across the West growing interest in water trading platforms and programs. Reducing the transaction costs for those types of programs is, again, important to allowing them to scale and be used more effectively beyond pilot applications and some limited applications across the West. And then finally, we know that evapotranspiration data is one of the key inputs into irrigation system design and irrigation scheduling. Increasing access to remotely sensed evapotranspiration data, we think can rapidly accelerate uptake of data-driven approaches for water management at the field scale. Our overall goals for the project are to ensure that reliable ET data are produced, operationally available for free or at very low cost, and easily accessible for any area within the Western US. That that users have confidence in the data, understand the accuracy, understand the strengths and limitations of the data, and that it's able to be utilized by water managers at just about any scale, from farmers and irrigators managing water for their fields to private and public resource managers at the local, state, and federal agencies that are potentially trying to plan water supplies at the basin scale for decades, over decadal timescales. And then finally, that the data is used to support a variety of sustainable resource management practices at a much larger scale than we've been able to do in the past. So I'll say a little bit about the OpenET approach and then pass it over to Justin to talk about some of the components of the architecture and the intercomparison. Everything we've done in OpenET has been user-driven, and something that the Environmental Defense Fund, Robin Grimm is unfortunately out of the office this week, otherwise she'd be here on behalf of EDF. But something they brought to the project from the outset was ensuring that the project was based on a user-driven design approach. We worked hard during the first year of the project to develop a series of use cases with partners across the West, ranging from small family farms to some of the largest agricultural operations in the West, from local scale water management applications focused on improving management of groundwater, to partnerships with the U.S. Bureau of Reclamation to try to evaluate different approaches for quantifying evapotranspiration across the entire Upper Colorado River Basin. So really looking at different applications for groundwater management, irrigation and crop management, regulatory compliance, watershed management, water trading platforms, and also at different scales and from the perspective of different types of users. So we'll talk about some of these as we go through the demo. If there are any that are of particular interest to anyone in the line, please let me know and we can talk about them in more depth as part of the question and answer. We've also worked with about 100 different folks, maybe more now, that have been part of our working groups for the project. And these include representatives from local water management agencies, agricultural engineering firms and consultants, conservation groups and other NGOs, farmers, again, from small family farms to some of the biggest agricultural operations in the West, state and federal water planners and regulators, and then also the agri-tech sector, including both startups and some more well-established organizations. And our goal has been to ensure that the data products we're developing and the way we're providing that information is going to be really quick and easy for them to use, and that all of the functionality we're developing is responding to a need that's been identified by one or more of our partners and potential future users of OpenET. We worked hard with the outreach. Early on, there were concerns identified by some of our agricultural partners around data privacy, around, is this just another tool that can be used against agriculture? We tried to be sure we listened really hard to those concerns, worked hard to address them. We've been doing a lot of outreach, and as we've gone through our soft launch and starting to plan for a full launch next year, we've been really pleased at the feedback that's coming back so far. So it's been great to see growing support for OpenET among the agricultural community, but also seeing support from folks like Joaquin Esquivel at the State Water Resources Control Board and Buzz Thompson at Stanford's Water in the West program. So I'm really happy with the initial feedback we've been getting. I'll talk a little bit about how OpenET works and then pass over to Justin. This is a sort of really simple architecture diagram, but everything all the inputs to OpenET are publicly available data sources, meteorological data sets. We rely heavily on the GridMet data set produced by the University of Idaho by John Amatsoglu's group, but also publicly available agricultural weather station data records, other weather station data records operated by NOAA and available through the Cooperative Observer Program, and then publicly available satellite data from USGS, NASA, USGS, NOAA, NASA, and ESA, the European Space Agency. Data is all brought into Earth Engine, and we use Earth Engine as a shared compute platform that allows the teams to collaborate and work together on pre-processing of all of the inputs. We can run all of the models there and then work together on evaluation, comparison of the models at a scale that we really haven't been able to do previously. Data is then stored in a geodatabase and on Earth Engine. We compute summaries for all of the individual field boundaries that we've been able to compile, again, from publicly available sources. And then data is distributed through an application programming interface and through a user interface, which we'll share with you in just a moment. We understand that for many applications, ET data is most powerful when it's combined with other information. And so we've developed an application programming interface, an API, to facilitate automated retrieval of data from OpenET and integration with other applications, whether those are existing irrigation management or future to be developed irrigation management and farm and ranch management software applications, local, state, and federal water data information systems, and then also water trading and water accounting platforms. And we have some nice already working examples, especially of the first and third case here, irrigation management and water trading and water accounting platforms, where we're already having partners pull data down from OpenET and integrate it into their applications and data systems. So let me pass it over to Justin to talk about the different models in the ensemble and the satellites we're using, and then say a little bit more about the intercomparison and accuracy assessment study. Justin?
Thanks, Forrest. Yeah, so essentially OpenET incorporates most of the more commonly used approaches for estimating ET. These models and approaches have been well established for many years and used in the community, both the scientific community as well as the practitioner and water management community for 20 years in some cases. So models selected for inclusion are, like I said, all been used operationally either by state or federal agency. And one major goal of OpenET is to avoid the scenario where different agencies are potentially using different numbers and obtaining different estimates as a result, and potentially causing confusion. And really, by bringing the science community together, as this project has allowed, that there will be a consensus estimate of ET through this ensemble estimate that we're developing, and essentially taking advantages of the strengths of each model. It's also fair to say that the state of the science itself is improving from this unique collaboration, thanks to the type of funding that we've received, philanthropy funding as well as NASA and USGS funding. It's really bringing together the community in a way that hasn't been possible before through traditional proposal competitive type projects. So it's really exciting that we're really advancing the science and collaborating instead of competing as done in the past. Next slide. So as Forrest mentioned, Landsat is really the workhorse for OpenET. That said, Modis, Terra and Aqua, and these other platforms listed here, especially NOAA-GOES for the dyslexia model, is really important for OpenET, as well as Sentinel, the ESA, Sentinel 2A and 2B satellites to help us get more frequent repeat and images essentially that we might not otherwise get from just Landsat alone to deal with cloud cover, etc. Next slide. So this is an image that we first created when we started to assess model results, where we subtracted CBOP from SIMS in this case, and we noticed that these red areas here are rice fields where SIMS is an NDVI-based model, and those fields were flooded, and NDVI goes down to near zero or even negative when you have standing water. And also you can see a lot of these blue areas off to the sides of the valley. This is northern Central Valley in California, where CBOP was low relative to SIMS. And so we saw this, we worked with Gabriel and Forrest, and essentially made improvements to the models to handle these conditions where we have really hot conditions on the sides, where CBOP was going low and SIMS was going low in these flood irrigated rice fields. So, you know, working together and not being, should I say, quote unquote, sheepish about what our models are doing, and actually working together to find the issues and fix them collaboratively has really been an awesome strength of the project. And it's been really nice to work with the modeling teams on this. Next slide. And so a really important piece of the intercomparison, in addition to the model-to-model intercomparison, is the intercomparison to flux tower data, as well as groundwater pumping records and basin scale water balances. So with respect to groundwater pumping records, we're using these pumping records essentially as a basic check, and also looking towards developing relationships between ET and groundwater use. And also how we can use these comparisons as a check against the groundwater pumping databases, and I'll illustrate an example of that in just a bit. Most importantly, though, in this intercomparison is our comparison across over 130 ET flux towers, aka micrometeorological stations that actually, well, it's a direct estimate of ET where we're measuring the vertical flux of water vapor leaving the land surface. And while these flux towers are really considered the gold standard for ET estimates, that's only the case if they're really maintained and well, set up well and maintained well. One thing to note is these are very expensive to set up. It's $50,000 just for the equipment alone, and that's actually a little bit conservative on the low side. And then another 50 to 100K a year just for ongoing operations and maintenance and data post-processing. There's a lot of things that you have to do with the data. And again, it's at the end of the day, it's just an estimate, and that only covers, in fact, about 10 acres of land. And also that there's no long-term historical data from these sites, because once you set it up, then you start collecting data. And so that's why having the satellite information is really, really needed here, because the satellite data both provide that space piece that we really need, as well as that temporal piece to go back far in time to develop these long-term water budgets and assess long-term water use. Next slide, please. I just will wrap up that slide by saying that together, all these different intercomparisons will be used to assess the model performance across different crop and land cover types, and will ultimately guide the selection of the models to be used in the ensemble. Next slide. Thanks, Forrest, for going back. And so here's just an example of one of the intercomparisons. Again, we have over 130 of these time series and one-to-one plots. We are going in and selecting the pixels that we're comparing to these towers by hand to make sure that we're selecting the right pixels using windrows diagrams, looking at wind direction and velocity. And in this case, you can see that there's one model that's estimating low ET compared to the rest, where the observed flux tower data is on the X and the model is on the Y. And it says closed here because we are doing energy balance closure with the flux towers. So the available energy never adds up to the turbulent fluxes. And so it's a common practice within the scientific community to adjust the turbulent fluxes upward so that we can close the energy balance. And essentially that means adjusting ET upward to close the energy balance. And that's what this yellow shaded time series is on the right. That's the unclosed ET and the fully closed ET. So the hope is that our models will fall somewhere within that yellow envelope, and you can see that most of them do, and there's one that consistently does not, especially during the growing season. Next slide. And it's not all good like that. So here's a site in southern Nevada that's essentially bare soil. It's Amargosa Valley near the Nevada test site. One of the models just is not designed to estimate ET from arid landscapes or non-irrigated lands. It's specifically designed for agriculture. And so you can see that these blue dots here where we're estimating quite high compared to the flux tower. So this is an extremely difficult site in the sense the ET is just low. And so the lower the ET gets, the harder it is for these models to estimate in general. Next slide, please. And then here's a rice field in the San Joaquin Delta where it turns out that the ensemble is the slope of the ensemble here is the closest to 1. We don't have a lot of data points at this site, but nonetheless, we are using this site as part of our intercomparison. So, it's really nice that we're using the Ameriflux network where we have 5 to 10 years of data for a lot of the sites, and a lot of the other research or academic operated sites by universities. They don't have as much data, but they're still extremely valuable because we don't have a lot of sites in rice fields, for example. Next slide. So here's a comparison to groundwater pumping data in Nevada, where we've been working with the Nevada State Engineer's Office to get pumping records. There's a lot of work involved in comparing ET to pumping records in the sense that you have to define the actual places of use, not just the water-righted places of use. And so oftentimes the water-righted places of use are defined by legal descriptions or township range section, quarter section, and that's what's shown here in the yellow box. And so what we have to do is go in and actually define the actual places of use, spatially average the ET data to these crop circles or the actual places of use, and essentially calculate a volume of ET and divide that volume by the area of the field to get a depth, or it's essentially the mean depth of ET over this whole field, and then use that same area and divide the volume measured by the magnetic meter in this case, magnetic flow meter, divide that volume by the area of the actual places of use to make a one-to-one comparison. I will say that a big difficulty here is just identifying what meter data goes with what area, and that it can be a one to many and a many to one type of relationship. So it's a big GIS exercise, but it's extremely valuable. Next slide, please. To be able to see how the ET data compares to pumping. So on the X is net ET or ET minus precipitation from OpenET, and the Y is the pumping, normalized by the area, so it's all in feet per year. And what you see are a lot of data points that are near zero in the pumping, but we actually had quite a bit of ET. These are areas in the database in which there was some question on whether that pumping was accurate or not. So going back through the database and looking at notes, it was pretty clear that these were erroneous geodatabase entries. Likewise, these yellow triangles are estimates of pumping that the state engineer's office made based on irrigation water requirements, based on a traditional Pima-Monteith and crop coefficient approach. And so that assumes well-watered conditions, and that's why we're well above a lot of these other data points that we see here derived by OpenET and the one-to-one line. So really interesting and a great way to be able to QA/QC these pumping records and then ultimately develop relationships between ET and pumping.
Thanks, Justin.
You bet. So
one thing I want to point out is I think when Justin and I started on this project, we thought we were just hosting a workshop, and we were lucky to have folks like Martha Anderson from USDA and Gabriel Sine from USGS join, and we had no idea we were going to end up conducting such a large and robust intercomparison project as part of trying to get things running operationally at scale. So it's been a tremendous team effort, and I know Martha and Gabriel are on the line. They've been long-term leaders in the remote sensing of evapotranspiration science community, and we're really lucky to have them as a part of the team. So I'll say a little bit about the schedule, and then while I'm bringing up the current alpha version of the OpenET Data Explorer, Gabriel and Martha, will see if you had anything you'd like to add or anything Justin and I missed. So in terms of where we are for OpenET, we just recently completed our soft launch, and the goal was to help ensure that folks in the agriculture and water management communities knew this was coming along and had time to reach out to us and make recommendations or suggestions and provide input into the development of OpenET. We are currently working towards a full public launch in sometime probably early spring 2021, definitely sometime next year. We will also be working on the development of a best practices manual, completion and publication or completion and submittal of the accuracy assessment and intercomparison study, and then also working on additional integration of the data from OpenET into operational uses with some of our use case partners. And I will pause there for a moment and see Martha and Gabriel if there's anything you'd like to add, and I will bring up the application as well here. And let's see, any questions so far, Deb, that we can address?
Nothing yet.
All right. All right. Okay,
Forrest?
so yes.
Sorry, I meant to unmute myself and I hit hang up instead, so I'm back on here. So this is Martha, and I just want to say that this is a tool that's going to be incredibly valuable for the end users, but I must say it's also incredibly valuable for the modelers as well. To date, we've been kind of reliant on these point observations of ET made scattered at very low spatial density across the regions we want to model. This ability to compare an ensemble of models on a fully complete spatial grid over such a large area is just an amazing opportunity for us all to learn more about our modeling systems and to identify issues we would have not even known were there without these intercomparison data sets. And it's also helped to build a really nice community, I think, amongst the modelers, where we might otherwise be competing with each other. Now we're working together to put out the best quality products possible. And I really have to credit both Forrest and Justin for setting the tone of this collaborative effort. So thank you.
Thanks so much, Martha.
Thank you. And we've been super lucky to have Martha and Gabriel as part of the science team. They've been a huge part of making this work and helping us establish this really positive collaborative culture as part of OpenET. Justin, is my screen coming across before I move on?
It is.
Great. Okay. So I'll admit the first time I saw this map, it brought tears to my eyes. I think it's really beautiful. Data, what you're looking at right now is over 4 billion data points. By the time we're done, we should have over 100 billion data points. The field boundaries are coming from either publicly available field boundaries from state agencies or from the USDA 2008 Common Land Unit database. A team at DRI has done a really incredible job of compiling all this and cleaning it up. Information is available, summarized for individual field boundaries, as well as wall-to-wall at that original 30-meter grid cell resolution, or 0.22 acres per pixel. Data right now is available for ET as well as NDVI as a diagnostic. Information is currently just available here from 2016 through present. The annual summaries, of course, just for 2016 through 2019. You can search for any location here with the search bar to help orient the user if they're looking for a particular location, or cities can be turned on and off. And we go back and forth between millimeters and inches to help serve both the science community as well as the agricultural community and the water management community. The legend here, just by placing your mouse cursor over the legend, will provide the information that corresponds to each color. But you can also go ahead and I'll just go ahead and zoom in here. Actually, let me look for Grand Valley, Colorado. There's another big part of this team that I forgot to mention early on has been Habitat 7. So something else that's been really nice about this project is the opportunity to collaborate with a just really committed, dedicated web development team that specializes in visualization of large geospatial data sets. So they've been a huge part of this project, and we've been lucky to work with them. So just now that we've zoomed in to about zoom level 12 or finer, the data is now being pushed from the geodatabase to the browser, from our vector tile cache to the browser. Just by placing the cursor over a field, it'll go ahead and provide the total annual ET for the year selected, crop type information based on the latest cropland data layer or information available from the states, and then the monthly time series for ET. I'm going to click on this field in particular because there's a nice story. This was part of a pilot. This field was enrolled in a conservation program. What we're looking at, I should say that when we click on the field, now that's hitting the geodatabase and actually retrieving the data live, both for the ensemble value as well as for all the individual models. So what we're looking at is the monthly ET time series. Each data point represents the total monthly ET going from January of 2016. We actually have data up through last month, up through August, but this is showing data through April of 2020 in this plot. Data is again available for the ensemble average. You can also, if there's someone who's been using one of these models for a water management application, you can also see how that compares. Each of these models compares to the ensemble mean and the ensemble range. And then there's ancillary data available. The reference ET, ET fraction, and NDVI are also available as a diagnostic. So we can see how those compare. But for this particular field, this farmer enrolled in a pilot conservation program and did not irrigate in 2017 and partially irrigated or only planted part of the field in 2018. And we can see how that affected their ET. Right? So we can see how did this conservation program result in a measurable reduction in evapotranspiration and consumptive use through ET. And sure enough, we can see here's the data for 2019, 2016, up around 34, 38 inches. 2017, the year they fully participated in the program, that was reduced all the way to 13 inches. And 2018, a little bit lower, 23 inches. So I think that was a result of partial planting. So that information is there. It can be easily downloaded, either as a graphic of the chart, as a CSV or Excel file. But an example of how we can use OpenET to quickly and easily assess benefits of various conservation programs and investment in conservation. You can also go look at, where should we go to next? Let's go look at Rosedale Rio Bravo irrigation. Water storage district. This is in near Bakersfield, California. And Eric Averett has been working with us to integrate OpenET data into a platform he's building to help his water storage district implement their groundwater sustainability plan as part of the Sustainable Groundwater Management Act. And so for Rosedale, a key component of their plan to balance pumping with water supplies and protect their groundwater resources is developing a water trading platform. And he's begun with rolling out a water accounting platform so growers can access information on their ET year to date in the same way they sort of check their bank account and get monthly updates on their balance. This has been rolled out to growers. They're checking it now currently. It'll run as a pilot program for a year or two, and then that'll serve as the basis for implementing a water trading platform in the future. So what's important to Eric Averett is really this ensemble value and getting past which model to use, which model's right, when does this model do well? Are there times where I should pick model A over model B? What he really wants to know is what is the ensemble value? What's the number that's recommended and represents the best available consensus view estimate from the scientific community that can be produced today? And so for him, this ensemble approach, the collaboration across the different modeling teams is what's really at the heart of the value of OpenET for his application. For this particular field we're looking at, this is a young almond orchard. We can see it progress from probably planting in 2014 or 2015 through first, second, and third leaf, and see how that evolution in the development of the crop canopy, of the orchard canopy, is affecting ET rates. This can be really important and beneficial for irrigation scheduling if folks are trying to really minimize the water they're using. In those earlier years, that's an important opportunity for water conservation, and OpenET can help them balance irrigation system applications to what's actually being lost through evapotranspiration. Another example of use specifically for irrigation management, we'll go up and look in Harney County in Oregon. Another OpenET partner and collaborator of Justin's has been Mark Owens, who's a farmer here in the Owens Valley and then also now a state representative. He worked with Justin and their team to actually set up flux towers in one of his alfalfa fields. I think it was this one, right, Justin?
Yes.
Sure, right one. And actually used ET data to go ahead and redesign his center pivot. He's reported reductions in applied water, reductions in pumping of about 15%, and that's resulted in electricity savings for him of more than 20%. And so this ability to account for year-to-year variability and adjust his pumping to actually match the ET is something he's really excited about for OpenET, and has been a really phenomenal partner for the project. And I think helping growers like Mark document the benefits, show how things are working, and serve as advocates for data-driven approaches to irrigation management in their communities, that's an important objective for OpenET, this ability to help water users, tell stories about their investments in conservation, and conduct outreach to other folks in their community. I think the last piece of this is supporting communities and having equal access to information to help work with regulators and water managers at state and federal levels to develop water conservation programs that are going to make sense for their community and represent a win-win solution. I'll pause there. Happy to go look around at other locations. I should also mention, of course, the data is available. I said this earlier, it's available wall to wall. So if there's a field where it's not included in one of the publicly available field boundary data sets, that information is still available and accessible. This is actually a query that's going out and hitting Earth Engine Live, searching through terabytes and terabytes of data to find this particular pixel, and then search through the archive of OpenET data and retrieve that. So given how much data it's searching for, I've really been amazed at the responsiveness of the system to pull out 4 complete years of ET data from a raster archive that's hundreds of terabytes large. So I'll pause there, see if there are questions or any places people want to look at. And thank you so much for those of you who joined for your time and interest. Deb, I can't see the chat window very easily in Teams here when I have my screen shared. Could you read me any questions or let us know if there's locations folks can look at? I'll say one last thing. We are also creating, through the API and the custom reporting tools here that are on, API is now being rolled out to partners for testing. Custom reporting tools will also allow users to upload a shape file or draw a shape to define a region of interest and get summaries for any time and location. So users are not just limited to accessing data through this data explorer. This is facilitated to make it as easy as possible, developed to make it as easy as possible for folks to explore data, get a sense as to how it's performing, see how it compares to their pumping records or other data sets they may have available. But the custom reporting tools and API are being developed to support more operational uses of the information.
Okay. So we're opening it up here for questions. We've got one coming in from Adel. Abdullah, do you want to unmute, Adel?
Hi, Adel.
Yeah, hey, Forrest, hey, Deb, and everyone, Justin. For some reason, the chat thing is not working here. It's been spinning forever. It's not allowing me to type anything. So great presentation. Thank you all for the hard work you're doing. There was a friend that reached out to me. We went to grad school together, and she thought that OpenET is going to be, I mean, she loved it and all that, but she thought it was free. It's going to be free. And initially I thought like maybe there's a confusion of like when it's open, between open and free. These are two different terms. And I'm not sure if you guys have that messaging somewhere that got buried, that it's for commercial uses, like, or if someone has a farm, maybe for a smaller scale, it is free, but like if you're build an app, it's not free, right?
That's a great question, Adel. So we are committed to, our primary objective with OpenET is to make the information available and easily accessible. And by far our first choice would be to make all the information freely available for all users. At the same time, it's also important to us that the product continues to be high quality, that the teams are supported to continue to improve the science, the code is well maintained, the application is robust and reliable. So we're trying to find that balance between how do we sustain a project like this that is a collaboration across so many different partners, with how do we maximize openness. The openness in OpenET refers both to the open science aspect of the project, where the models are open source, the things are well described, we're conducting open and transparent accuracy assessments and intercomparison studies, and we're making data available through the Data Explorer. We're committed to do that without question. We are currently working and talking with state and federal partners about how we might be able to support this long term. I'm guessing a number of folks on the line have confronted this problem over and over again. which is when we develop a new capability, especially when it's a collaboration across multiple partners, how do we support it? How do we sustain it in an era of flat or declining budgets? If we were looking at growth every year, I think it becomes a lot easier to think about creating space in our budgets to support new technology, new information systems, new products that we know are going to be useful to the public entities and private entities that we serve. So our current thinking with OpenET is that we want to have a diversity of sources. We want to provide as much data in a freely available way as possible. But we are anticipating that for large-scale commercial uses of data, especially when the commercial partner is reselling it, that we will likely have a paid tier within the API. So if it's a farmer just wanting to evaluate the data, or a family farm, or maybe even a medium-sized agricultural operation, there'll be a large free tier available so that those types of users will be able to access all the data they need. But if it's a really large commercial entity with substantial resources, we hope they'll be willing to contribute to the long-term ongoing maintenance and development of OpenET, especially if they're reselling the data at a profit.
Great. Okay.
Thanks, Forrest.
Justin, anything you'd like to add to that?
No, that was well said, Forrest. Thanks.
Okay. I have a question coming in from Brent Duncan with NRCS. He asks, does the interface access data other than the imagery or ET model output?
Yeah, I'll go ahead and share my screen again. Let me share that. So, yeah, let's go look at a field in Diamond Valley as an example.
While Forrest is going there, I can chime in. Ultimately, this geodatabase includes not only ET, but also American Society of Civil Engineers reference ET, the Pima-Monteith reference ET, as well as NDVI, and also irrigation status, whether the field is actively irrigated, non-irrigated, uncultivated, so we can start to summarize the ET by irrigation status. And we are going to be adding precipitation soon, and then also crop type is already included.
It's important to note that the field boundary data sets and crop type, we're only using publicly available sources. And the field boundary mapping is a project in and of itself. And of course, USDA has the operational cropland data layer program. So we're primarily pulling data from that program, except in cases where state agencies have their own program and have expressed a preference for our use of their state data. But here's just to show an example. Here's the ET time series, the reference ET from the ASCE, grass reference ET calculated from the GridNet data, and then NDVI from Landsat, monthly NDVI from Landsat. And we will be, as Justin mentioned, adding precip and potentially other variables based on feedback from our users and partners.
Okay. Any other questions out there?
I'll just say that we welcome suggestions, we welcome feedback. We've been really grateful to USGS and the Water Availability and Use Science Program for their engagement and thinking about ways to use this as part of the Water Availability and Use Science Program. AUDL and the Western States Water Council, we did a briefing, similar briefing for them last week, and engagement with state partners has also been extremely valuable. We have a number of state partners that have been part of our working groups and part of our alpha testing groups for the Data Explorer and API. So we really appreciate the partnership with the council, with the member states, and with our other federal agencies. None of this would be possible without this collaborative effort.
Yeah, and I'll just add to that, Forrest, with respect to collaboration with Reclamation,
Thank you.
Jim Prairie and the Upper Colorado River ET study that he's conducting, and also our long-term collaboration with the Technical Services Center at Reclamation, and just how valuable I think this is, will be to the Technical Services Center as they move forward in estimating consumptive use for different projects. For example, just yesterday I talked with engineer Mark Spears, trying to design or working to design a small reservoir for a tribe in Owens Valley, Independence, California. And just simply being able to go in and look at what the ET is for a nice well-irrigated alfalfa field to get a depth of ET that could be expected to at least use as a starting point to start to design a reservoir. Just really simple things like that could otherwise take a really long time to deal with. And I feel like that's kind of the why now, is that, until now, it's been really hard to estimate ET. And now that we have Google Cloud Computing, we have operational ingest of all the satellite and gridded weather data that's happening every single night. They handle all that maintenance and operational ingest for us. I mean, we're using about 10 different gridded data sets in tandem together. And to think that a single state agency or a single federal agency will do this on their own, and keep it operationally up to date, it's pretty daunting given the petabytes of data that it requires. So it really is a whole new time and paradigm for us right now, in that we have the ability to scale.
And I just want to second that acknowledgement for Jim Prairie. Jim has really helped frame our thinking about how we present the intercomparison. Folks like Jim and Eric Averett at Rosedale Rio Bravo, and why it's so important to not just be able to identify places like up here near Idaho Falls, where the models really agree well, but also identify places where they don't agree well and explain those differences to the user community. So to help them understand not just where there are differences, but why they occur. And then also to provide those recommendations for which approaches to use for different applications. So that case study with Jim for the Upper Colorado and Sarah Larson at the Upper Colorado River Commission has been really, really important to thinking about how we present the results from the ensemble and intercomparison study.
Great. So this is Deb again. I have a follow-on question coming in from Brent Duncan. He says, I understand ag land is primarily flat. However, do you think there could be a benefit to using elevation data to produce 3D visualization through the interface, basin views?
Yeah, like that could be powerful, and something we could add in the future. I mean, the map layers and map tiles could be, you could imagine exporting them to other 3D mapping applications. We're trying, I mean, one thing, there's so much that could be done. Sorry, I thought my camera was on. I must have, apologies. There's so much that could be done. We forced ourselves to really follow this user-driven design approach. So only implementing tools that are being identified as important for multiple users, just because otherwise you could build an incredibly complicated system. So we're trying to find that balance between simplicity and functionality, and working with this set of roughly 100 use case partners has been, I think gotten us to a good balance so far. I will say, to build on Justin's comment, that it's important to us that OpenET is valuable for all of our federal partners and federal agencies. And I know a number of folks at WestFAST have been involved in the research to operations workshop. This is a great example of why we need to solve that problem, right? How can we work together as federal agencies to adopt and operationalize new capabilities in a way that's time efficient, cost effective, and streamlined? So we welcome thoughts and recommendations from anyone on this call for folks to reach out to and conversations we should have.
Okay.
We need help from WestFAST on solving that problem for sure.
Any other comments or questions? Yeah, I think that's it, Forrest.
All right.
So
Thanks.
thanks everyone for joining, and especially thank you, Forrest and Justin, for your presentations. And I hope everyone has, oh, hold on, someone's got something here. Oh, no, it's Michelle saying thanks. So everyone have a great day.
All right. Thanks all.
Thanks much.
Thanks so much.
Thanks, Deb. Thanks, Otto. Bye all.
Bye-bye.